we will look at a few specific examples. So one example is the process of numerical integration. So just like in that previous example, maybe this is an acceleration signal and we want to estimate velocity. Or conversely, maybe this is a velocity signal and we want to estimate position. So this signal isn't necessarily something that we can represent by a standard function, an exponential polynomial. We're not driving our vehicle according to ax squared plus bx. And so in order to perform this integration numerically, we need to think back to what integration means graphically. And graphically, an integral is an area under a curve. And so a way that we can estimate this area under the curve, one simple way, is to basically take the curve and split it up into a bunch of rectangles. And so the area of these rectangles, if we sum them up, can be used to estimate the area underneath the curve. One thing that you'll notice is that this will introduce error, just like we were sort of anticipating. This rectangle sort of underestimates the area under the curve. This rectangle sort of overestimates the area under the curve. If the error in our signal is random, or if the signal itself sort of moves up and down, then these errors will often sort of cancel each other out. Here we underestimated, here we overestimated. Those two errors approximately cancel out. However, if there's a bias in the measurement, so if the blue line is the true velocity and the dashed red line is what our sensor is giving us, then we calculate this area. The longer we integrate for, the more this error builds up. And so this can be a real issue, and it's something we need to be careful about. If we have a bias in our measurement, numerical integration can introduce a large amount of error. And so a situation where this might occur could be, for example, let's say that we're using GPS somehow in our control algorithm, a GPS signal, a global positioning satellite. Maybe we're a bus that's traveling a certain route and we're trying to keep track of where we are along the route. But if for some reason the bus goes in a tunnel, or there's some sort of weather interference and that GPS signal drops out, then we may have to find a different means for estimating our position. For example, we may integrate our wheel speed signal, or our estimate of the velocity of the vehicle. We may integrate that to estimate the position of the vehicle. But if we have to do this integration for too long, the error can get quite significant. Another example of this is submarines. So a submarine, it goes under the polar ice cap, or to sort of evade detection by another country or something. And it has to stay under the water for a month. That whole time it's trying to sort of estimate its position by integrating a velocity signal, maybe from a gyroscope, so that it knows where it is, so it doesn't run into land or an iceberg or something. And so you can imagine, even if your velocity signal is very accurate, if you have to integrate it for a month, that error can really build up. And so there are quite advanced techniques for estimating this bias or compensating for this bias. Another type of signal processing that is often done is numerical differentiation. So again, let's say that we have a velocity measurement, but what we really want is an estimate of acceleration. So you could take this velocity signal, differentiate it to get an estimate of acceleration. But just as was the case previously, the signal, our velocity signal, doesn't match some known function. And so what we have to do is we have to numerically differentiate. And so think back to what a derivative is graphically. What a derivative is it's basically the slope of the tangent at a given instant of time. A simple way to estimate the derivative is to calculate the slope between two points, or two data points. And we get an estimate of the derivative, in this case of acceleration. And so as you look at this again, at any given instant, the slope, the instantaneous slope, doesn't exactly match the slope between those 2 points. So again, this approach to signal processing introduces error. If our measurement signal has a bias to it, that bias won't introduce a large amount of error. The slope of the true signal is the exact same thing as the slope of the measured signal. However, if there's a lot of noise, for example in this signal, and we're estimating the slope between 2 points, you can imagine that this noise will introduce a lot of error. In fact, differentiating that noise can, in essence, amplify the noise. So this is something that you need to be very careful about if you're numerically differentiating or differentiating a noisy signal. This is one reason why people are often sort of hesitant to use derivative control in their controllers. And so this is something we'll come back to later in the semester and talk about how to deal with it. Another type of signal processing that can introduce error is analog to digital conversion. So for example, we had that example where we had some continuous signal, an analog signal from a sensor, and we wanted to read it into a digital computer. And so the simplest way to do that is to simply sample that continuous signal periodically and hold that value. So let's say we're sampling every 10 milliseconds. And so over that 10 millisecond period, we're just going to hold that value. Doing that introduces error in a couple ways. One is it can introduce time lag. So in essence, if I sample the velocity of my vehicle and I hold it for a period of time, by the time that I get to the end of that period, the velocity estimate I'm using is in essence old. It's no longer what the true velocity of the car is. The car has changed speed since 10 milliseconds ago. And so this lag can degrade the performance of a control system. And this is something that we need to understand. Something else that analog to digital conversion can do is it can introduce quantization error. So for example, you can imagine the number pi. Pi is an irrational number. In order to express it exactly, you need an infinite number of decimal places. But this would require, a computer that has more memory or computational power than exists. So at some point within a computer you need to round off, and this introduces quantization error. Whatever processor you're using has a limited amount of precision, has a limited number of bits, and so at some point you have to round off your numbers. And so here is a piece of data from an experiment that we're actually going to do in this class, measuring motor speed. And you can see that the motor speed is sort of jumping around between these three discrete values, 450, 464, and 436, let's say. The speed of the motor isn't actually jumping back and forth between these three discrete values. It actually is moving at a relatively constant speed. It's just that the speed is getting rounded between these three values. Okay. So this brings us to the conclusion of Module 8. In this module we discuss sensors. In particular, we discussed examples of electromechanical sensors, sensors that are able to bridge the electrical and mechanical domains of our control system. We also talked about how they must be considered as part of a larger measuring system, that the output of a sensor may need to be processed in some way, and then it may need to generate an output or be read into a computer. And so each stage of this measuring system has dynamics and can introduce error, and we need to understand those. We discussed in this module a few different examples of signal processing and how they specifically introduce error, and how we must be careful when we use them in our larger control system.